So we are starting again. We have an invited talk today by Romain Maggiolo. I butchered it. It's of the Roleau Belgium Institute for Space Astronomy. Sorry.
Thank you, and thank you for inviting me to a very interesting workshop. So I'm Romain Maggiolo. I'm a space physicist with no background on machine learning. But here I will present you the result from a recent project we had with two other colleagues, Benjamin Grisant in Prague and Fabien Darroze in the same institute as me. So we replied to an ESA call and made the manual classification of magnetospheric and near solar wind regions for the cluster mission. So here I will just present you this database, how it's made, the goals, the way we did it. And I will focus on its specificities and compare it with automated classification. And after that, I will present you the potential applications of such a handmade database. And so this is more personal view. It's a summary of a small project I introduced in spring, which is under review. And it's how we see it as scientists, how it can be used, those kind of classifications, to help us do science. So the idea is that when you have a spacecraft orbiting in the magnetosphere or around the magnetosphere, its spatial location doesn't really tell you where it's located in geospace, so in which region it is located. So it's due obviously to the interaction between the solar wind and the magnetosphere, which is dynamic, so to the driving of all the process by the solar wind, but also to internal processes like storms, substorms, that makes all regions dynamic and moving and not always located at the same place. And also inside one specific region, the plasma properties can also vary depending on the tons of process that can happen in the magnetosphere. So the story received from ESA, it was like 3 years ago. They wanted to have the location of the cluster spacecraft, which is arriving at the end of its operating time. So the location of the satellite with respect to the main magnetospheric regions. Cluster, so it's a set of 4 satellites that operated for more than 2 decades and that have 11 instruments on board. So the cluster data set is just huge. And when scientists want to use such kind of data, they spend a lot of time browsing the data to find interesting events or to identify regions if they want to make statistical studies. And one particularity of the cluster mission was its polar orbit. So thanks to this polar orbit with a perigee around 4 ARI and an apogee around 19 ARI, is that it crossed the main magnetospheric regions. And of course, because the orbit stays in the same plane, so you have on the left the orbit in summer, on the right in winter. So with this, we really sampled many regions with 4 satellites. But it's really a lot of data. And so ESA made the call in 2022. And I think they expected someone to come with an automated method. But I think we were maybe the only one to answer this call, maybe because the money was not so big. And we proposed to do it manually. So it was accepted by ESA with some constraints, so that the data set, the region should really be directed towards scientists to help scientists use cluster data. And so we did this classification. Now it's available on the Cluster Science Archive. I will come back to that later. And it was made by human operators. So most of the job was to define the regions, their properties, and to make a detailed guidelines for those operators who had to browse through this more than 20 years for 4 satellites, so around 100 years of data, and click every time they were identifying a change of region, so a boundary, a kind of boundary. So of course, this implies a lot of constraints, and that's why, I mean, That's one of the reasons we choose to limit the resolution to 20 minutes. So anytime you enter a region for less than 20 minutes, we don't tag this as a new region, but we have ways to take that into account. One specificity of this database also is the definition of a transition region. So a transition region is not really a boundary or a boundary layer. It's somewhere in between two regions. I will also come back to that later. And something that we understood we had to add later, during the process, is a complexity tag. So 0 means the region is exactly as you expect it to be, and 1 means you understand you are in a given region, but its properties are a bit different from what you expect. So to do this classification, we use 44 different data sets. It can either be time series, like the magnetic field, plasma density, or velocity, or spectrograms, so time energy spectrograms, pitch angle spectrograms, wave spectrograms. And this was made by a visual inspection. So we downloaded PNG files, so figures from the cluster archive. And we developed a non-made software to display those data and to allow the operator to click when the spacecraft was changing region. And why do we use so much data set? It's also because some physical parameters can be obtained or derived from various instruments. For instance, if you think about the plasma density, you can get it from the ion measurements, from the electron measurements, from the waves with the plasma frequency, but also you can derive it from the spacecraft potential. So that gives some complexity because depending on how the instrument is aging, on the operating mode of instruments, on the region where you are located, maybe some way to get the density is more accurate than the other. And to understand that, it requires a lot of visualization of data. It's not so obvious, or you cannot really directly know which estimate of the density is the best. So often you need to compare one parameter obtained from different instruments. And from those data, we defined 15 regions. So one of the constraints from ESA was that we need to have, for any moment, a tag that tells you where the satellite is. But sometimes you don't have data or you don't have enough data. So we have some tags, which means void, no data, unknown, we could not identify the region. Outside, which means we know we are outside the magnetosphere, but we don't know if you are in the solar wind or magnetosheath. Same for inside, you know you are inside the magnetosphere, but you don't know where. That can be if you have only, for instance, magnetic field measurements and no other data. And then we have a set of regions. So in purple, it's inside regions, and in light blue, it's outside regions. And you see this TR, which is for transition region. So that's an example of a transition region, which is really, I think, a specificity of this data set. So you can go from one region to another if everything is static and you see a change of plasma parameters, like at the magnetopause, it can be smooth or less smooth. That's really a boundary. But what can happen, because the boundary is moving and sometimes your spacecraft is skimming the boundary, you can be inside the magnetosphere and then inside, outside at a very short rate. And that's impossible for an operator to identify this manually. And also sometimes you just have partial crossing of the boundary. So that brings some complexity. So our decision was to say, we define a transition region and we know that the boundary itself is within this transition region, but it's not only the boundary in the transition region. It can be the two adjacent regions that are there. So here you have an example. The spacecraft is going from the plasma sheath to the magnetosheath. So here, okay, see it on the screen, but here you can see plasma sheath plasma, hot, energetic, magnetosheath plasma, lower energy. There are differences in magnetic field, in velocity, but in the middle here you see something very messy. So maybe it's the properties of the boundary, maybe it's the boundary moving with respect to the satellite. So that's an interesting period. You know that the magnetopause is somewhere there, but you cannot really identify it. So that's how we define this transition region. And because to be fast enough, we had to give a lower time resolution. So we say the operator, 20 minutes is the minimum duration of a region. So this is approximate because, of course, it's handmade. So basically, the operators had 3 panels like that on their screen, and they were clicking every time there was a change of region. It was made by students, so of course we had to be very careful that they knew what they do. It required a lot of checking and training. It's not training a machine learning or an automatic tool, it's training a human. But it worked pretty well. And from that, we are now finishing the last 2 years. So we get the location of cluster spacecraft in different regions. So here an example, it's Brian plots. So the vertical axis represents 1 orbit and the horizontal axis, the number of orbits. And you see with time, the difference between what a static model tells you and what we get from our region identification. So these 2 regions are Bow-Shock and Magnetopause, where you expect them to be. And this dot is where we find them. So we see that it's dynamic and that it's not because you know where you are in space that you know in which region you are. That's the same kind of plot, but with a color code for all regions. So what you see here, which is like, say, the winter season for cluster, it's spending a lot of time in the solar wind. And then later, close to summer, it's spending more time in the inner magnetospheric region. And what you see, for instance, so in yellow here, it's the Bow-Shock transition region. So it's the Bow-Shock is somewhere there. Sorry. Okay, it's back. So of course, it's human-made, so it required a lot of validation. So we had some warnings. For instance, you cannot go from the solar wind to the plasma sphere, which is well inside the magnetosphere. So if we had this succession of region, we did another check to be sure to identify where the aurora was coming from. We had some statistical tests looking at plasma density, plasma beta, whatever, and we compared with the existing database. And actually, we were quite surprised, a good surprise, because we had really a quite good agreement with the existing database, either handmade or made automatically. And actually, most of the difference comes from our time resolution. We have 20-minute time resolution. We have a transition region, but maybe some other method with a shorter time resolution will go from one region to another. So basically, on average, the classification worked pretty well. So we heard about that this morning. There are nice studies that made automatic classification. So that's an example from the Breuer et al. Paper. So what we see as a difference with our manual classification, you can have a quick alternance of region. So you have your tool, it's checking data and tells you I'm here, I'm there. And this can change at very short time space. There is no complexity time. So either you are in the plasma sheath, in the low region, whatever, but it doesn't tell you if it's standard conditions or if something special may happen. So this database is available on in open access on the ESA cluster archive. So if it's an archive when you can access cluster data, but also the result of our classification as if it was a data set from a instrument. And we published a paper at the beginning of the year that can be used as that describes all the method and all the parameters and information we give to the operator. So it's really a user guide, actually. It describes the data set and how to use it. So if we summarize and compare our classification with automated classification, what I can say it's very slow to click on 100 years of data, and many students came and worked on that. And it's made by humans, so there are errors. Probably classification is made better in the morning compared to 6 in the afternoon. You take two different operators, you give them the same data, they give two different results. So reproducibility is not that good, that perfect. But it also has good sides that it's subjective and made by human, because after some time, the operators could identify weird things. And actually, that's when I started. That's something I was doing very often, looking at a region and trying to find some data that seems to be weird or showing that something unexpected happens. If you compare that to automated classification is way faster and has a better reproducibility. But then there are some challenges to make automated classification. So how do you deal with degraded or evolving data? When it's a human looking at data, you can see, like, for instance, the ion detector is less and less efficient and get used to that. How can you identify something that you don't know with an automatic method? Something that is different or special, that can be challenging. And how to make this classification user-friendly for scientists? Actually, something which is human-made is easy to be used by a human. 20-minute resolution, it's fine. If I'm a user and I want to work on the plasma sheet and I have an interval of 1 minute in the plasma sheet, what can I do with that as a scientist? I need the context, I need measurements before and after. So doing it manually actually was also interesting, because it tells you, what is needed by the user, which I think in the end is the one that is the most important, and how you will use it. So once we did this classification, we had the idea to use it. So the basic use is for scientists. So it saves times. You want to study the plasma sheets. Plasma sheets in our classification is something like 15% of the time clustering in the plasma sheets. So you just look at 50% of the data instead of looking at all the data. We developed some tools which are more for students to visualize the regions. So either you have cuts. So here, for instance, is where we identify the magnetospheric. This is where we see the solar wind foreshock. And from that, you can do statistical studies, for instance. So not just to an illustration, but in blue, you have the density in the lobe region, in red, in the plasma sheath, and in green, in the plasma sheath transition region. So it's the interface between the plasma sheath and the lobe region. It contains some plasma sheath intervals, contains some lobe intervals, and it contains the boundary, the transition. But then we thought, can it be used for other things? And an obvious thing is to train and help training and validating machine learning classification. So that was one idea. And in particular, one thing which is very interesting for scientists is we have there were many missions studying space physics and plasma physics around the Earth. And all those satellites, they bore more or less the same kind of instruments. Magnetic field detector, electric field detector, ion electron detector, wave instrument. And those instruments, they are a bit different, but not so much. So the data sets you get from cluster, THEMIS, double star MMS, and maybe in the future plasma observatory, they are not that different. The resolution is improved, things are improved, but it's the same kind of data. So they are common in a field that I don't know very well, but the idea was that if you do classification on the ground, you are less limited by resources. You have time, you want a uniform classification over different missions. You can use a lot of data. Most of these data are available on database. They are validated, calibrated. So you take your time, you put all the resources you need, and you can probably easily reach a classification that is uniform and that can be used by scientists. So now what people do, they say, okay, I want to study the plasma sheet. I look at cluster data. Then I go to check Themis data. That takes a lot of time. The idea is like, I want to study the plasma sheet. I run a shortcut and I have all the time periods where one satellite is in the plasma sheet. Could be cluster, Themis, MMS, whatever. You have your data in the plasma sheet. Then you can cross-check the times and you can say, oh, this time I have 4 satellites in the plasma sheet. That can make a very nice study. I have measurements in different places. So that's a very obvious and straightforward application. And another one, I think it has been discussed this morning by Maria Frederica. Those satellites, they have a lot of instruments. They produce a lot of data, and we make better and better instruments with better resolution, and so producing more and more data. And the bottleneck is telemetry. You can have your instrument working in burst mode at the maximum resolution. It's fantastic. You have wonderful data, but you cannot transmit them to Earth, to the scientists, so they may be lost. So what you do, you have operations that are usually planned with quite static models, and you say, okay, the magnetopause where you have quick change of the plasma properties is usually there. So you take a 2-hour time interval around the expected location of the magnetopause, and you do burst mode, and then you transfer this to Earth. But of course, it's not very efficient. Maybe in these 2 hours, only 10 minutes were actually at the magnetopause. So we don't use the instrument at their maximum capacity just because we cannot transfer the data. And so we need a way to select the data. So for MMS or Valanon probes, there were more complex methods to select the data to download, but it remains not fully automatic and also a bit too static compared to the medium you are measuring. So the idea, I had this idea and knew nothing about machine learning. In fact, that should be very easy. It's not. And the more I learn, the more I see it's complicated. But the idea is to have onboard classification that classifies in a way similar to the GRMB database that we built. So it tells you in which region you are. It tells you if you are in a transition region, and you can add a complexity tag. Say, okay, I'm in the plasma sheath where I spend a lot of time, but this time something weird happens. That's very interesting data. I want to transfer them to the ground. It needs to be prioritized. Or you can have measurement campaigns. Cluster had some measurement campaigns in the oral zone, for instance. For a few months, you focus on this region. If you know on board where you are, of course, you optimize such kind of campaigns. But then comes the problem. First, I realized that resources are limited on board the satellite. So you cannot do as you do for ground classification. But also you have to place that somewhere in your satellite. So that's a schematic representation of the data stream in the satellite, like cluster. So you have your set of instruments. Some instruments require a processing unit inside the satellite. For instance, an ion detector, you have the processing unit that ingests magnetic field data and ion data, and then you have your distribution function, your pitch angle distribution, so distribution with respect to the magnetic field orientation. So you have some computing on board. And what we would like to do, or at least what would be useful for a scientist, is to somewhere catch those data, use a machine learning tool that will tag the data. So it will just add the amount of data you will produce is pretty low. It's just a tag, a number as we had before. Number 1 is this region, number 2 is this region. You may add a complexity tag, like we are in this region, but something weird is happening. And you attach this tag to the data and you send them to the data handling unit. And it's just an information. If you want, you don't take that into account and you proceed as usual. Otherwise, and that can be decided on the ground and that can be modified during the mission. You say, okay, I want a complex event in the plasma sheet. So I will give priority to the data that have this tag, number 15 and 1, for instance. And you give priority for data downlink. You could change that during the course of the mission. Say, okay, now we want to focus on this or that, or you see that it doesn't work very well, so okay, we don't use it anymore. So that gives you a lot of flexibility, and I think also some people will appreciate that it's still fully under human control, because it's very risky actually just intercepting the data in the satellite. So it's something on the satellite that grabs the data, read them, tag them, and send them to the satellite is a risk. So if you do that, you will need redundancy. You will need to have a second set of space wire to transfer the data in case your tool that accesses the data has an issue and stop the data stream. Because if you stop the data stream, the mission is over. Another possibility is to put your tool in the data handling unit, but then it's not where you place instrument usually. So that's more like where the spacecraft operates, and that gives you other complications. Especially space agency don't like scientists to put something there because it can put a mess or can make problems. So actually the tool itself can be simple, but just implementing on a satellite is complicated. But I think as a first step for classification, it's pretty safe. It gives full decision to humans. It doesn't work, you get rid of it. So I think it's really targeting safety, and which for me means that it could be implemented faster on a satellite. So to conclude, we developed this GRMB database, and if you're interested, I encourage you to use it to test, validate, train your machine learning classification tools. This tool has been handmade, which has good and bad sides, but it has really been tailored for scientific use. And of importance are transition regions, complexity tag, and not a too short resolution. And scientists often like to develop their own tools. So if they know there is a transition region, which is like 1% of the orbit, where they will find magnetopause, they will work on this subset of data, and they may develop some homemade tools to identify the magnetopause, so just threshold criteria, whatever they want. But scientists will know that how it's done, how it's identified. It won't be a black box anymore. And so we thought about potential applications. One direct one would be multi-mission classification that is uniform. And for the future, it could be onboard classification to optimize data downlink, which will allow scientists to receive more high-resolution data for periods of high scientific interest. And to implement it quickly, I think what is important is that it may still, at the beginning, under full human control. Space agencies. And I'm done. Thank you.
Yeah. Questions?
I mean, I'm not a magnetospheric person, so I have like a set of questions for you. First one is like, are all the 4 spacecraft on the same plane?
No, they form a theta-hydron, because like this, you can compute the currents, the gradients. But of course, it depends on the orbit. So
which kind of a volume they space?
It does change over the mission. Spacecraft separation went from a few kilometers to hundreds of kilometers, depending on what you want to see. If you want to see small-scale currents, you will bring them close. Or if you want to study magnetopause, which is a very sharp transition.
I guess then that influences your results.
We did that spacecraft by spacecraft individually, as if they were completely not related.
Yeah. So, and another question was, because you have a time resolution of 20 minutes. So how much is done associated with this spatial resolution? Because your spacecraft is moving in time. So how much they pass because.
So of course it's fast.
Averaging that.
Perigee.
Yeah.
that varies over the 20 minutes. Velocity is a few kilometers per second. To perigee, I think. So it's not so big. And also it really depends because things are in the magnetosphere, it's mostly controlled by the magnetic field. So if you go along the magnetic field, finally you're almost at the same place.
Yeah.
If you go across, then you can cross several regions in 20 minutes.
Yeah, this is why I was wondering about this time resolution, because basically maybe due to the time resolution which you pre-select, you will see only certain type of structures. And
No.
or you will see certain type of structures more often, and the other one you will see.
The idea really is to make just a pre-selection. So when we say we're in the plasma sheath, we are sure it's in the plasma sheath. If someone wants to see all plasma sheath interval, yes, this person has to take plasma sheath and plasma sheath transition region. Some plasma sheath intervals are there.
How thick is a plasma sheet? I mean, I'm not.
It varies all the time because
yeah, because
when you close to the Earth, it's quite stable.
You're so certain you're on a plasma sheet, but I mean, if you have so much resolution, time resolution, which actually bases the spatial resolution, so how do you know that?
So we also have the lattice complex. So usually when you enter the plasma sheet, you have this transition region that allows you to handle the motion of the plasma sheets. Then you enter the plasma sheet. You should stay in it until you cross it and you reach the other transition region. So if inside the plasma sheet where you're supposed to be, you see another region, it's not normal. Something happened, and we tag it as plasma sheet complex. So maybe there was a substorm, there was reconnection nearby, there is a burstable crew, whatever, that changed the topology, the local topology of the plasma sheet, but you know something happened. That's why first we introduced this complexity tag, and then we extended it to anything that is unusual, because I mean, we send the satellites to discover new things. So if in advance we say, yeah, that's it,
Yeah.
How can we find new things? So sometimes you have to say, that's not usual, complex. Maybe there is a new process, a new thing to discover.
You have so many years of data. Did you try maybe to see if you have some differences? Because you know that we have the in situ spacecraft data like ACE or something. And then you can actually know if there is an event which happens, which impacts the Earth, to select those ones from to tag them using the wind or ACE data as the storm events.
Yeah,
and select them.
That's something very usual for us. So we have tools for that in France or in other countries where you can get data from different missions and make selection of data. For instance, you want periods of CMEs, you have a list of CMEs, you have a timetable, sorry. You take this timetable and you say, I want all cluster data during this period. So we have tools for that, but it's really manual. You click, you open it.
No, I mean, the definition of in situ CME, I mean, ICME, or fast wind.
Yeah. And I would say from my personal point of view, I don't really like when it's too automatic because I want to know how it has been selected. So I prefer to do sometimes my own tool with its errors and weaknesses, but at least I know exactly what has been done to select the data. That's why we try to be very general in our classification to leave a lot of freedom to scientists. Because I'm in the French data center, which is developing this kind of tools for users. And we realize that we make very nice tools and people don't really use it. They prefer developing their own tool. So
funding issue, I would say.
Yeah.
Maybe the last one. Just you showed the figure where you said, okay, you have a here transition. One of the first figures, something happens. It looks to me, it looks like compression of field.
Can be so many things. Can be directly driven by the solar wind. You have compression, depression. You can be related to internal processes. You have a substorm. Magnetopause will move. You have low frequency waves, the magnetosphere, you have alpha waves, you have whatever you want that can make the boundary move with respect to the satellite. you cannot really know in advance what is the driver of this motion. You have Kelvin-Helmholtz instabilities on the flanks. You have many things that build this transition region. And with 4 satellites, you can know if it's spatial or temporal, if you are with the good geometry, which is not always the case.
Let's thank the speaker again.